Welcome to course on mechanical behavior of materials part 2. So in the last lecture, we completed the topic on deformation of composites. Today we will talk about uh, toughening of ceramics. Okay, so let's talk about that. So these are the general properties of ceramics. So you can see strength of ceramics are typically high. I hope you know a little bit, fundamentals of ceramics. This has been covered in the basic courses of material science and engineering. Okay? So it has a relatively higher strength, then hardness is also high. Wear strength is also high, or wear resistance. Chemical inertness is also high, right? So these are some of the good properties of ceramics. However, the problem is with the fracture toughness. So the fracture toughness of ceramic is low. Okay, and that is what there is a limitation of ceramics for structural and non-structural application because of their poor fracture toughness. Okay, so what we are going to discuss is how we can use the microstructural design to improve the fracture toughness of ceramics. Okay, and that's what we call as toughening in ceramics. Okay, so here I have shown the comparisons of different materials. So you can see fracture toughness in the x-axis, right? So ceramics has the lowest fracture toughness among plastic, composite, and metals. And as usual, metals and alloys are going to exhibit the highest fracture toughness among these four kind of materials. Okay. And traditionally, most of the ceramics are going to be single phase monolithic. And I already mentioned that they are going to exhibit poor fracture toughness. Okay. So on the right side here, I have listed fracture toughness values of some of the materials. So you can see alloys, okay, ceramics, monolithic ceramics, and then you have toughened YSG. We'll discuss about that later, how we improve the toughness in ceramics. Okay, and there we'll discuss about YSG, which is yttria stabilized zirconia. Okay. So if you see, the alloys typically are going to exhibit very, very high fracture toughness. So extruded AG31 magnesium alloy has 28 MPa root meter. And then titanium 6Al4V, which is one of the famous alloys in titanium, that has about 71 MPa root meter. And if you see ceramics, so all these aluminum oxide, glass soda lime, silicon carbide, either hot pressed or sintered. So depending upon the processing conditions, your fracture toughness might also vary, right? So if you see silicon carbide, it varies from 4.8 to 6.1 depending upon the processing condition. Similarly, silicon nitride, so it is 4.1 to 6. Okay. But if you see, ceramics have lower fracture toughness as compared to metals and alloys, right? Now the last one, which is YSG. So you can see there is an improvement of the ceramics. So if you have only zirconia, it is going to exhibit very poor fracture toughness, but you add 3 mole percent of yttria and the fracture toughness is going to increase significantly to 7 to 12 MPa root meter. And that is what we are going to discuss, how we can change the microstructure, right? So that the toughening in the ceramics can be obtained. Generally, ceramics have lower fracture toughness. Okay. So these are the two papers. There are many papers, but these are the two papers I found by Professor Ricci. And it is about the toughening mechanisms in solids. Okay. So this is the first one, which is published in Philosophical Transitions of Royal Society A. So in 2021, toughening materials enhancing resistance to fracture. Okay. And he has listed all the toughening mechanisms which can be used in ceramics to enhance the toughness. Ceramics as well as composites. So in different materials overall. Okay. And this is the old paper in 1999 published by Professor Ricci in International Journal of Fracture. And this is also related to the toughening mechanism, basically extrinsic and intrinsic mechanism. We'll discuss about these two mechanisms shortly. Okay. So in ductile and brittle solids, both. So if somebody is interested, you can go through these two papers and very nicely described about how you can increase the toughness of a given solid. Okay, we'll discuss some of them in today's lecture. Okay, so intrinsic and extrinsic mechanism. So if you see, I have written something. So it says the track growth occurs as a mutual competition between intrinsic and extrinsic mechanism. Okay, so there are two mechanisms are acting. So if you have a crack, right, there could be a stringing mechanism and extrinsic mechanism. Okay, what is intrinsic mechanism? It's a microstructural damage mechanism which promote crack extension ahead of the crack tip. So intrinsic mechanisms, by default, they are going to promote the crack extension ahead of the crack tip. Okay, and that is the material property. So material is going to show you intrinsic mechanism. Like if you talk about metals and alloys, they are going to show you slip activities, right? Right? Activation of slip systems. Okay, similarly, void nucleation and growth. Those are inherent, right? So those are intrinsic properties or intrinsic mechanisms which are going to promote the crack extension ahead of the crack tip. Now the second is extrinsic. So these are the shielding mechanisms which primarily act behind the crack tip. Okay, so they are going to act in this region primarily. Okay, remember intrinsic is going to act ahead of the crack tip. Okay, and extrinsic is going to act in the wake of the crack tip. Okay, so this is, say, intrinsic. Okay, and in the wake of the crack tip or behind the crack tip, you are going to observe extrinsic mechanisms being activated. And these mechanisms, extrinsic one, they are the shielding mechanisms. They are going to somehow, reduce the stress intensity factor at the crack tip so that they are going to restrict the movement or propagation of the crack. Okay, so intrinsic, they are going to promote crack extension. Extrinsic, on the other hand, they are shielding mechanisms and they are going to retard crack growth. Okay, they are going to reduce the crack tip driving force. And what is crack tip driving force? That is stress intensity factor, right? So they're going to reduce that and therefore they are going to retard the crack growth. So these are the two mechanisms you are going to observe in the given material. Okay, so I have one link here. Let me show you the image. So the title is Toughening Mechanisms in Nano-Layered Mass Phase Ceramics, a review. So it's a review paper, okay, and it's published in 2017 by Shen. And if you see, so this is what I wanted to show. So if you see this, it says schematic illustrating both intrinsic and extrinsic mechanisms of toughening mechanisms associated with the crack extension. Okay, so you have a crack here. So this is your crack, right? And as I mentioned, the extrinsic mechanism by nature, they are going to be acting in the wake of the crack. So in this particular regime, whereas intrinsic mechanisms are going to be activated ahead of the crack tip. Okay. So you are going to see plastic zone formation, which is intrinsic mechanisms in metals and alloy system, right? You are going to see activation of slip systems. You are going to see microvoid coalescence, right? Those are intrinsic. Cleavage fracture. Those are the nature of that particular system. Okay. So they are going to promote the crack growth. On the other hand, extrinsic mechanisms, you are going to see these being activated in the wake of the crack, like, side wedging. I will discuss this in a bit. Similarly, grain bridging, fiber bridging. This we discussed when we were talking about toughening in metal matrix composites, especially ceramic matrix composites. Okay, so all these grain bridging, fiber bridging, or side wedging, and there are some more mechanisms. They are going to reduce the stress intensity factor ahead of the track tip, and thereby they are going to retard the track growth rate. Okay. Remember, if you draw the line of forces or stress lines, you're going to see that some of those lines will be transferred to these fibers, these grains, and then the oxide wedging. So overall, the stress concentration in front of the track tip is going to reduce, right? Because this air in the track way is going to be replaced by all these microstructural features. Okay, so what are the different toughening mechanisms we have in the solids? So let's talk about that. So overall, you have to somehow increase the energy, right? Or you have to spend more amount of energy for track propagation. And if you can do that, you're going to increase the toughness, right? So key is to spend more energy for track propagation. Or you need to reduce K at the track tip. Okay. So let's go one by one. So the first is track deflation. And we discussed this point in metal matrix composite also. And rendering. Okay. So you have a track and then they are going to deflect if they see some particles. Okay. Or some phase, some particles. Right. So if you see in metal matrix composite, we had this track deflation when the interface was weak. Okay, so that is track deflation. So this is your track here. Okay, and now when the track is being deflected, the track length is becoming higher. That means you are spending more energy for track propagation. Point number one here, this point. So as soon as you do that, you are increasing the toughness of this solid. Okay. So this is point one. Second is zone shielding. And in this, we are going to have three different mechanisms. First one is transformation toughening. Second one is micro crack toughening. Okay, and third one is crack void, crack filled void formation. So these will come under zone shielding. Okay. So what is transformation toughening? So here you are going to transform in situ some phase to another phase, which will lead to a compressive stress in the wake of the crack. Okay. So in situ, we'll discuss this shortly when we will talk about partially stabilized zirconia. There you will understand what is transformation toughening. Okay. So in situ transformation leads to compressive stress in the crack wake. Okay. So as soon as you see the compressive stress in the trackway, obviously you are going to reduce the driving force for track growth, right? The overall stress in front of the track tip is going to reduce the tensile amount of it, right? So that is point number one, transformation toughening. Second is micro crack toughening. Okay, so you have a crack, okay, and then say you have some phase here, okay. Now, because of say transformation toughening or the phase itself, they are going to crack or interface is going to crack. So what is happening? You are going to form some amount of cracks. Say something like this, right? So the formation of these cracks by themselves are going to require some amount of energy. So you are thereby increasing the toughness. Now, second, as soon as the main crack is reaching towards the interface, they are going to observe these cracks, micro cracks, and they are going to merge, and thereby they are going to get deflected, right? That will also contribute towards the enhancement of the fracture toughness. Okay, so this is happening because of the formation of micro cracks. So micro cracks of say precipitates, some particles, okay, or interface ahead of the crack tip, okay, leads to enhancement of fracture toughness. Okay. Why? Because of the formation of crack themselves will require. Second, this main crack can merge with this micro cracks leading to the deflections. Okay. The last is your crack filled void formation. Okay. So you have a crack and then you have say form some voids, right? And this void can form when you have say some ductile phases which can lead to the void nucleation and then growth and coalescence, right? Or the void growth actually. Yeah. Okay. So if you have higher number of voids, you are going to require higher number of energy to form those voids. And therefore, the fracture toughness is going to increase. Okay. So these are the three mechanisms: transformation toughening, micro crack toughening, and then this crack filled void formation. Remember, all these three are related to um, somehow the spending of more amount of energy in the material or reducing the crack tip driving force, right? But you don't see the crack surfaces, touching each other. That means this, if I say this is crack surface 1, crack surface 2, they are not somehow touching with something else, right? Okay. So this is like you're shielding the zone. And that's why the name is given as zone shielding. You're somehow shielding the zone, especially in the weight of the crack tip. And that's why you're reducing the crack tip driving force. Okay. And, I'm going to talk about again this transformation toughening and micro crack toughening when we talk about partially stabilized zirconia. You will understand it better there. Okay. Now the last one here is contact shielding. So now the cracks are going to be in touch with some material in between, like we had discussed about in fiber reinforced composites, right? Where you saw that the fiber bridging concept, right? So there were fibers in the track, and therefore it was leading to the fiber bridging, and therefore the stress intensity factor ahead of the track tip was reduced. Okay, so that is contact shielding. That is a third mechanism. So first one was your track deflation. Second one was zone shielding, and last is contact shielding. Okay. So here you have wedging. Okay. That means you have a crack, and then you have, say, some corrosion products. Okay. So corrosion debris. So that is number one. Debris induced crack closure. Okay. So what is happening here? If you remember, you have a crack, and when we discussed about the stress intensity factor, stress concentration, right? We had this all lines, imaginary lines coming like this. And why were these were deviating? Because they were finding air in this particular region in the track, right? And air cannot transfer load. So they were just deviating this line of forces, leading to the concept of stress concentration. We discussed this. Now, if we somehow place, some material here, which is solid, and they can transfer load, right? So it is possible that some of these line of forces will be going through like this. Okay. And this will lead to the reduction in total number of line of forces, right? Or stress concentration. Think about it, right? Imagine it. So this will reduce the stress concentration in front of the crack tip here, right? And that is the concept of contact shielding. Okay, you are now having a contact with of these two track surfaces. If this is track surface 1 and 2, with something, some solids which can transfer the load from track surface 1 to track surface 2, and thereby it will reduce the stress concentration factor or stress concentration in front of the crack tip. So one is corrosion debris. So you have some corrosion debris which is going to reduce the crack tip driving force. Second, track surface roughness induced closure. Okay. So your track surface itself is rough. Okay, something like this. And it is touching at some point. See, at these points, these 2 points, your track surface are touching, right? So again, some of the loads will be transferred through these 2 points, and therefore, at the crack tip, stress concentration will be reduced. Okay. So this is about wedging. Now we have bridging, which we have already discussed in composites, fiber reinforced composite, where we talked about fiber bridging. Okay. So you have a crack, and then you have lots of fibers. Okay. Like this. So it's like bridging, right? And again, from these fibers, you can transfer the load from top surface to bottom surface of this particular track, and thereby you are going to reduce. So see here, the difference between contact shielding and zone shielding. In the zone shielding, you're not having any contact, right, in the wake of the track. But somehow, which we'll discuss, you are actually having the compressive stresses in the wake of the track in zone shielding. And thereby, you are reducing the track growth rate. Okay, or driving force for the crack growth rate. In the contact shielding, you have contact here in terms of either corrosion debris or roughness induced or fiber bridging. And because of that, you are reducing the stress intensity factor or stress concentration in front of the crack tip, and thereby overall retarding the crack growth rate. Okay, there is one more plasticity induced crack closure, which works on the concept of both zone shielding as well as contact shielding. Okay, I will not discuss that in detail. If somebody is interested, they can go through some of the books. It is has been nicely explained in many books. Okay, so this is what I wanted to discuss about the overall toughening mechanisms in a given solid. Okay, so remember contact shielding is acting in the weight of the track, right? Zone shielding is also acting in the weight of the track and some also in front of the track tip. And then track deflection is also there, right? So these are the general mechanisms. Okay, so intrinsic and extrinsic. We discussed about this before. Now we also know overall toughening mechanisms. So let's summarize. So intrinsic mechanism is an inherent property of the material, like cleavage fracture, ductile, and then slip activity, then void growth, coalescence. These are inherent property of the material, right? And these will be active irrespective of the length of the track or geometry of the test specimen, right? So if the track length is small or large, doesn't matter. These are intrinsic mechanisms. They will be activated. Although the strength or the magnitude might be lower or higher depending upon the track, but they will be activated. On the other hand, extrinsic mechanism, these are predominantly acting in the weight of the track, right? So these are acting here. Okay? And they are highly depending upon the track length. So if your track length is larger, think about your fiber brazing case. So if your track length is higher, that means you can have more number of fiber brazing as compared to if your track length is lower. So it is highly dependent upon the track length, these extrinsic mechanisms. Okay. There is obviously no effect on the track initiation of these extrinsic mechanisms because there is no track weight, right? And if the track is small, right, then it is not very important. It is more, active if you have higher, larger track length. Okay, so this is the difference between extrinsic and intrinsic mechanisms. Now, if you compare the toughening in metals and ceramics, so metals, by nature, metals are toughened intrinsically, right? Slip activities. If you have commercial alloys, then you have all these phenomena of void growth, nucleation, etc. Right? So metals are toughened because of mainly slip activities. Right? And that's what it's written. It's through mobile dislocation activity to induce a significant plastic zone size. So they have by nature good slip activity. And that's why they have a good fracture toughness. Their ductility is also very good. Okay? However, under cyclic loading, extrinsic mechanisms are also important. Fatigue track closure, we have not discussed it. If somebody is interested, they can go through what is fatigue track closure. But just to point out here that under cyclic loading, metals can also show extrinsic mechanisms. Okay. On the other hand, ceramics, negligible plasticity, right? A very small, very, very little plasticity. So negligible contribution from intrinsic mechanism. By nature, ceramics will show very small or no plastic deformation. So if you want to increase the toughness, it has to be predominantly extrinsic in nature, right? So you can have transformation toughening, which we'll discuss shortly in terms of partially stabilized zirconia. You can have uncracked ligaments, unbroken reinforcement phases in composite or laminates, like you have cracked bridging, right? Fiber bridging. So you have ceramics matrix composite, you have fibers, then you see fiber bridging there, right? So you are actually using extrinsic mechanism to enhance the toughness, isn't it? And then you can also see micro crack toughening in ceramics. Okay, so these are the predominantly three mechanisms by which you can enhance the toughness in the ceramics. Okay, so let's talk about phase transformation induced toughening. And you must have heard about partially stabilized zirconia, tetragonal stabilized polycrystals, zirconia toughened alumina. Okay, we also say yttria stabilized zirconia, YSG, right? So these are related to the phase transformation induced toughening, right? So you are transforming the phases, and because of that, so these are coming under zone shielding. right? Remember that zone shielding? So there will be no contact of the track wake, but you are inducing the compressive stress because of the phase transformation, which will lead to the retardation in the overall crack growth in a given ceramic. Okay. So let's talk about partially stabilized zirconia. So here I have mentioned cubic matrix plus tetragonal phase dispersion, right? So if you have partially stabilized zirconia, you are going to see at room temperature cubic matrix and tetragonal phase. And when you apply the stress, this tetragonal phase is going to convert to monoclinic phase, which will lead to the increase in the volume, or locally there will be dilation. And that will lead to the compressive stress in the weight of the track. Okay, I will discuss it now in details. Okay? So if you see pure zirconia, they are going to have three allotropes. So you are going to observe cubic, that is at high temperature, then tetragonal, then monoclinic. Okay, and monoclinic is stable at say room temperature. Okay, so when we cool it down, and if I take pure zirconia, when it cool it down from say high temperature to room temperature, and when it transforms from tetragonal to monoclinic, there is a huge dilation. There is a huge volume expansion, about 4%, and this leads to thermal cracking. Okay, and therefore, making pure zirconia is also not very easy. Because of this dilation, there will be cracking. So you cannot actually make pure zirconia. So what we can do if you want to increase, so that means, pure zirconia is going to have very, very low toughness, right? So what we can do, we can add CaO or MgO, okay, or Yttria or Syria, some oxides, right, which are going to produce a different phases at room temperature. Okay, so you say if we add nearly 7 to 8% of CaO in Yttria, and you can go to the phase diagram of zirconia and CaO, you will see that nearly at about 7 to 8% CaO, if we add, the room temperature microstructure will consist of tetragonal plus cubic phases. Okay, so if I add 7 to 8% CaOA in zirconia, you go through the phase diagram of zirconia and CaO, binary phase diagram. So you are going to see that at room temperature, the phases will be cubic plus tetragonal. And that is what I have written here. So you are going to have cubic matrix and tetragonal phases will be dispersed. Okay. So there will be two phases, right? Now, when you have the stress application or when you have a crack, okay, and suppose you have the matrix, which is cubic, and then you have a dispersion of tetragonal phase. So these are your tetragonal phase. These are dispersed in the cubic matrix, and there is a crack which is approaching, which is say propagating, right? So we know that if there is a crack, there is a stress concentration in front of the crack tip, and because of the application of stress, this tetragonal phase is going to convert to monoclinic. Okay. And as soon as this phase converts to monoclinic, you are going to see a dilation of 4% locally, right? So say this phase has been transformed. Okay, this phase now has been transformed to monoclinic. So now I am changing the color. Say this phase has transformed, this phase has transformed because of the stress. So locally, you are going to observe dilation locally, right? But cubic phase is there. Now, what will happen? The cubic phase is going to observe compressive stresses, right? Because this tetragonal phases which have transformed to monoclinic, they are going to expand it, right? But cubic phase is there. So what is going to happen? They are going to have compressive, right? Now think about it. You have a crack here. Now you have all these transformed particles of phases in the wake of the crack. You are going to have compressive stresses, right? And that is what the concept of zone shielding is. You are actually shielding, right? And that is happening because of the phase transformation of tetragonal phase to monoclinic phase. You are increasing the volume, and thereby locally you are having the compressive stresses, and it is acting in the wake of the crack. So this is the concept of zone shielding, and thereby you are improving the fracture toughness of the zirconia. Right? So pure zirconia has very, very low toughness, but if you add CaOA or MgOA also going to show the same kind of behavior, right? So it depends upon the what is the phases, composition and the fraction of phases at room temperature, right? So if you have cubic plus tetragonal, then you are going to observe this kind of phenomena there, right? Tetragonal stabilized polycrystals have approximately 100% tetragonal phase. Similarly, if you say zirconia toughened alumina, right, that also has very, very high toughness, that is ZTA, right? So there you have alumina and we are adding zirconia. Now what will happen? This zirconia is tetragonal phase, then it is going to have in front of the crack tip, it is going to convert to monoclinic, and that will lead to the increase in volume locally, and therefore it will induce the compressive stresses. That is point number one. Second, if the stresses or if the compressive stresses is large enough, you can see cracking, micro cracking. So ZTA, zirconia toughened alumina, can show both. It can show phase transformation induced toughening, and it can also show micro crack toughening. Okay, so you can have the compressive stresses as we have discussed just now for partially stabilized zirconia. Similarly, you can also have cracking, right, locally there because of, say, if the compressive stresses is higher, right? So this locally the interfaces can crack, and that will lead to the micro crack toughening. So ZTA can show both micro crack toughening as well as transformation induced toughening. So here I have summarized, if you see, so you have a brittle ceramic. This is stress strain plot. Okay, and this is the toughened ceramic. So if you want to measure the toughness, what you have to do, you have to take the area right under the curve. And you can see brittle ceramic is going to fracture here, toughened ceramics is going to fail here, the area under the curve, toughened ceramic is going to be higher, right? So here I have also listed some of the mechanisms. So you have fiber reinforced, so glass and carbon, silicon carbide, fiber reinforced composite. See the fracture toughness, 20. And remember the glass one, it was very low already. Silicon carbide also is low, but because of the fiber reinforced composites, now the fracture toughness has dramatically increased to 20. Right? Similarly, you can have viscous reinforced to 20% here, 10 and 40. Right? Now you can have ductile phases, so alumina, and then you have aluminum as ductile phases. Transformation induced, so you can have partially stabilized zirconia, see the toughness, 18, right? It has improved, and all is happening because of the transformation from tetragonal phase to monoclinic phase locally, okay? Then you have tetragonal zirconia polycrystal, zirconia toughened alumina is 10, so you are improving it because of the transformation. And then ZTA, as I mentioned, it can also show you microcrack toughening, right? If the locally the stress is higher, right? Similarly, you have silicon nitride and silicon carbide. There also you can observe the microcrack toughening, but it has improved, but it is only up to 7. Right? But overall, if you see all these mechanisms, these are extrinsic mechanisms, and they are improving the toughness of the ceramics. Okay, so this is how overall you can improve the toughness of ceramics. Okay. Now let's complete this topic by describing about the fatigue in ceramics. So we have completed, the topic on how we can improve the toughness. Now I think it is clear, stressing and intrinsic mechanisms. Okay. So here I have a link where I will show you the difference between ceramics and alloys fatigue crack growth rate. So this is again the same paper, Mechanisms of Fatigue Crack Propagation in Ductile and Brittle Solid 1999, International Journal of Fatigue, Professor Ricci. So if you see the first picture, the first image, this one, okay. So you have high strength steel, then you have aluminum, lithium alloy, then this is for titanium alloy, right? Intermetallic, you can see magnesium PSG, right? So you have for metals, intermetallics and ceramics, right? So typically if you see ceramics are going to exhibit higher crack growth rate as compared to the metals. So metals are on the right side and ceramics are on the left side, right? So typically ceramics are going to observe higher crack growth rate. Okay, that is what this particular curve shows. Okay, so during fatigue, you are going to observe crack growth in ceramics, that is 0.1. So, there is no plasticity that we have discussed in ceramics unless you improve the toughness by some extrinsic mechanism, right? So, it was thought that it might be due to the environmental effect, this whatever you observed in terms of the crack growth in fatigue, right? However, later it was found that ceramics are also susceptible to fatigue even if there is no environmental effect, okay? And the sensitivity to the crack growth to the stress intensity is extremely high. Okay. So the exponent M, the Paris law, if you remember, right? It can grow to very high value, 15 to 50 or above also, as compared to metals where it was 2 to 4 an alloy, right? So now the same thing, what we discussed in the metals when we talked about the toughening, in metals, the cyclic process are predominantly intrinsic, right? In metals. So while we are talking about fatigue crack growth, you remember that was inherent to the metals, right? However, I mentioned that you can also see crack-induced fatigue crack closure that we have not discussed. That is extrinsic mechanism. But predominantly, metallic systems are going to show you intrinsic in cyclic processes, right? Whereas ceramics, the fatigue processes are extrinsic in nature. Okay. So here the cyclic loading acts to diminish the shielding in the crack way, right? So you are going to have predominantly the extrinsic mechanisms are going to affect the cyclic processes in the ceramics. Okay, but when you have more number of cyclic loading, what you observe that there is a diminish in shielding in the crack way, and this lead to the increase in crack tip intensity factor, and therefore you have very high crack growth rate in fatigue of ceramics. So this degradation in the shielding mechanisms can take various forms depending upon the what is the shielding mechanisms is acting, right? So the examples are premature fatigue failure of metallic reinforcement phases in ductile phase toughened materials, or the reduction in the effect of fiber bridging in fiber reinforced ceramics matrix composites, right? So fibers they have broken, so you are going to reduce the effect of fiber bridging. So as you increase the number of cycles, there is a reduction in the shielding, right? And therefore crack growth rate increases. Okay. So I'll stop here. We have discussed about the toughening mechanisms, which is one of the important concepts in ceramics, and then very little bit about the fatiguing ceramics. Okay. In the next lecture, we will finish the topic of fracturing polymers. Thank you.